Good morning, students. We have already covered torque on a loop placed in a uniform magnetic field. Today we discuss current loop as a magnetic dipole and its dipole moment. Students, you know that when a bar magnet is placed in a magnetic field, suppose you take this is a uniform magnetic field and you place a bar magnet like this, or you place in electric field, suppose this is electric field, and you place a dipole like this. What you say, electric dipole? What happens? This rotates. That means in this case a torque is produced. Exactly. If you place a current loop like this, here is a current loop, what will happen? The current loop rotates. But if there is no magnetic field, this current loop does not rotate. So what does it mean? So since it carries some current, that's why it behaves as a magnetic dipole. Why we so called a magnetic dipole? Because when it is placed, it rotates like your dipole. That's why we say this current carrying loop is a magnetic dipole. So since it is a dipole, it will have north pole, it will have south pole. So which one is taken as north pole? I mean, if current in a loop is seen clockwise from a phase, suppose from this side we see this is clockwise, I mean this side is south, the opposite side is what? North. Suppose this is the loop, you see current is clockwise, so this phase is your south and this phase just opposite is your north. So since it is a dipole, it has dipole moment, and this dipole moment capital N depends on your current I, what current it carries, depends on its area, means this is the area of this loop. So if you combine, you will get N is proportional to Ia. A constant is there, that is Kia, but this constant is taken as 1 by experiment. So what you get? M is equal to I into A. But if this is N number of turns, so it will be NIA. So this is the magnetic dipole moment of a current loop. And this current loop is nothing, this magnetic moment is a vector quantity, you know. So in vector form one can write N vector is equal to NIA vector. So here the direction of the dipole moment is along area vector. A vector means area vector. So what we know, a current loop behaves as a dipole, hence it is taken as a dipole. Like your bar magnet, it has dipole moment. This is the formula. And also this is used, you see, when we have already deducted torque in a loop placed in a magnetic field, there we use this M in place of NIA. N is the number of turns, I is the current, and A is the area vector. Okay.